Hey guys, today we're going to review what are logarithmic and exponential functions. Let's start with an exponential function. An exponential function is any function where the variable is expressed as the exponent of any base. So here are some examples. For example, we have 5 raised to the x is equal to 25, and 3 raised to the 2x plus 1 is equal to 38. These are exponential equations because we have our variable as part of the exponent. Now, in our lesson that we're going to be doing later on derivatives of exponential and logarithmic functions, we're going to also work with the base e. So a base is the number that, or variable, whatever, that has the exponent. So for example, in this equation, the base is 5, and here the base is 3. So the common base e is represented by the irrational number 2.71828, etc. Now, it's an irrational number just like pi, so e represents a number, and it is used as the base of many exponential functions. This is the graph of e, just so you can see how that works. So e, like for example, this coordinate here, this is e to the 0, and anything raised to the 0 exponent is equal to 1. Here, where x is 1, that's e to the first power, right? Because this is e to the x, so if x is 1, I plug in 1 for x, and we get the 2.718, etc., etc. And then this would be e squared, which is 7.389, etc., etc. Now, a logarithm is defined as the power to which a number must be raised to get some other value. So a logarithm is the inverse of exponential equations. So for example, if I have here the log with a base 2, that's what that little number is, of 5, that's going to equal, or equals x, that's equivalent to the exponential equation 2 raised to the x is equal to 5. So this number here, that's the base of the exponential equation. And then what this is that 2 raised to what number would give me 5. Just so you can understand that a little better as well, here I have the ln of 3. Now, ln, that is your natural log. So basically, another way of writing ln would be log with a base e. And in this case, it would be 3 equals x. So if I wanted to write this as an exponential equation, it would be our base e raised to what exponent is equal to 3, which is what I have here. And this is the graph of ln. Now, this should be an x. So the ln of x is equal to log base e of x. So the ln of 1, that's going to be 0. And the reason why the ln of 1 is equal to 0 is because our base e raised to the exponent of 0 is going to equal to 1. Because anything raised to an exponent of 0 is 1. So that's why we have that coordinate there of 1, 0. Your ln function has a vertical asymptote here at x is equal to 0. It's never going to touch that x is 0. And also, we can't have the ln of a negative number. So that's why it goes only on the right side. Now, I just wanted to highlight a couple of things from log and ln and e. But let's look at their relationship. So an exponential equation, as I said, is when you have something raised to our variable is equal to our number. So this is b raised to the exponent of x is equal to something such as a. And this can be translated to our logarithmic equation, which is log base b, right? Here's my base, b raised to the x is equal to a. So I do a spiral when I am translating from exponential to logarithmic or logarithmic to exponential, and it helps me kind of organize my work here. So for example, if I have here the exponential equation 4 to the third is equal to 64, then I would write this as log, now my base is 4, so that's the little number here, of 64 is equal to 3. So if I just had log base 4 of 64 is equal to, let's say, x, then what you're doing is you're trying to figure out 4 raised to what exponent gives me that 64. Now, if I want to translate this logarithmic equation into exponential, I would start with my base always, which is 5. And again, I'm going to do a spiral. Raised to the negative 2 is equal to 1 over 25. And this should be true, right? Because if you have a negative exponent, that means that the 5 is going to go down to the denominator and become a positive exponent. So this here is 1 over 5 squared, and 5 squared is 25. So you see, I hope you can see the relationship between our exponential and logarithmic equations. Now here we have the exponential equation 10 to the third is equal to 1,000. My base is 10. When you're writing your logarithmic equation, if the base is 10, we don't need to write the base because that's implied when you just use log. You only write the base if it's another number. So I don't need to write my base there. It's implied that it's 10. So it's the log of 1,000 is equal to 3. Translating this logarithmic equation to exponential, my base is 2 raised to the negative 4th power is equal to 1 over 16. Now we can do the same thing given variables, and it's the same process. Here, again, I start with my base, so this is the log of base 2 over 5 of y is going to equal to the exponent, which is x. Now let's try putting that in exponential. My base is 1/3 raised to the exponent of y is going to equal to x. Here we got 3 to the 5th equals 243. If I want to write that as a logarithmic equation, I start with my base 3 of 243 is going to equal to my exponent here, which is 5. Last one, we have log of x is equal to 3. Since I don't see a base, that's implied that the base is 10. Raised to the exponent of 3 is going to equal to x. So that's how you can convert from exponential to logarithmic or vice versa. Now we're not going to need to do that for our lesson where we're finding the derivatives of e and log, but I wanted you to understand what they are. Now we're going to look at properties of logarithms because this we are going to be using in our lesson for derivatives. So our properties of logarithms are ways that we can get our logarithmic expression and either condense or expand. So these are those properties. This is what we've been looking at already. We don't really need to worry about these right now, but if you have, the first is a product property of logs. If you have a log of base, whatever the base is, of some functions m and n being multiplied, then you can actually expand the logarithm so that it's log base b of m plus log base b of n. So if you are multiplying functions, then the property to expand would be to separate the m and n and add it. Now if it's dividing, so this is the quotient property of logarithms, then it's the same thing, but instead of addition, it would be subtraction. If you have the log base b of m raised to some exponent, then this exponent becomes the coefficient of the logarithm. So you see how the n was moved to the front here. And then this is the change of base of logarithms, which we won't need to use for our derivatives, so we can disregard that last one. So let's look at how to expand and condense. Here I have log of x minus 5 log of y. This is expanded because we have the subtraction. As long as the logarithms have the same base, we can use these properties. Even though I don't see a base, that means that both of these have a base of 10. Since we have a coefficient in front here, that means that I can move this coefficient and it will become the exponent of the y. So we got log x minus log of y to the fifth. Now this is subtraction. And when you're subtracting, that means that the logarithm was being divided. So this is going to equal to log, and it's always the first is over the second. So log x over y to the fifth. Now here we have log of xy squared over z. This is condensed. And now what we're going to do is we're going to expand. So everything that's in the numerator here, this is being multiplied. So that means since it's being multiplied, that is addition. So we would do log of x plus log of y squared. And now the z is divided, so division is subtraction. So minus log z. Additionally, because I have this 2 as an exponent, I can take that 2 and move it to the front. So my final answer would be log x plus 2 log y minus log z. Let's practice that a little bit more. So we're going to either expand or condense depending on how the logarithm is written. So here we got 2 log, oops, this is supposed to be an x, minus 8 log y. The numbers here, these are exponents. So I'm going to condense. So this 2, I'm going to make it the exponent of x, and the 8, I'm going to make it the exponent of y. So this would be log of x squared minus log of y to the 8th. Because this is subtraction, that means that when I condense, and again, they both have the same bases, since it's implied that it's 10, this is division. So log of x squared over y to the 8th. For b, here we have ln. Now, ln is the same thing, like we use the same properties of logarithms because even though it says ln and it doesn't say log, remember that ln is just the natural logarithm. It's the log with a base of e, so we can still apply the exact same properties. So inside of this natural log, we have x times y to the third. So since this is multiplied, that means that I can separate it. I'm going to expand and add these two together. So it'll be ln of x plus the ln of y to the third. Additionally, this exponent can be moved to the front. So ln of x plus 3 ln of y. And that would be my final answer. For this next one, we have the ln of x to the fourth over y. So now here this is condensed and we're going to again expand. So division, that implies subtraction. So this is the ln of x to the fourth minus the ln of y. And this 4, my exponent, can be moved to the front. So 4 ln of x minus the ln of y. In this last one, we have 3 log x plus log y minus 2 log z. So here it's expanded, and now we want to condense it. All of these coefficients can be moved as the exponents. So this is the log of x to the third plus log of y minus log of z. What's being added, that means that that's being multiplied. So log of x to the third y. And then here we have minus log z. That means that the z is divided. And this is condensed. And that's logarithms and exponential functions.